we talked about curves and surfaces, and it is important, for example, to think, for example, about an image as a surface. Okay, so if we think about an image, about the XY coordinates of an image as the XY coordinates, and the intensity at each and every point is the can be thought of a third axis, then you can think of an image as a function, as in fact as a surface, where the coordinates of the surface are the x, y, and the z-axis is nothing but the intensity. It is easy to think about an image this way, and I think that Ido showed you. I mean, this would be a white circle on a black, a white something on a black background, okay, Gaussian, for example, because it allows us to think and invent geometric filters to this kind of an image. So if a gray level image is nothing but a two-dimensional surface in a three-dimensional space, x, y, and the intensity, then a color image can be thought of as an RGB. I mean, these are three functions that maps the x, y coordinates into the RGB space. At least this is the common way of now producing, for example, screens and projectors and computer, and then your iPhones are all these projectors are based and screens are based on the RGB space. Okay, so what would it help us to treat images like that? It would help us because then we can actually, and then I would jump over all these kind of stuff, because then you can think of each of, for example, of the color images, of the color functions, the red, green, and the blue, as being, for example, Lambertian. If we think about the image as one that is where each and every point in the image is proportional to the inner product between the normal of the surface that we are picturing. So assume that this is my picture and I'm looking at an object here. And as we said, the color at each and every point that is being projected onto this image is proportional to the angle between the normal of the surface. So this would be the normal of the surface and the light source direction. Assume that this is the light source direction. Okay, so the color at each and every point in the image is nothing but the cosine of this angle between the light source and the normal. And if we look at the color image and the object that we are looking at is not reflective, but rather specular, not specular, but rather Lambertian or diffusive, for which this law of projecting the light source to the normal applies, then we can look at the color image, where now for each and every point there is a scalar, and usually the scalar is the same for the same object, that multiplies the red, the green, and the blue channels. Okay, so we obtain three functions: red, green, and blue, and the red, green, and blue channels should be the same scalar if the object has the same color times the cosine of the angle, times this inner product between the normal and the light source. And the question is, how can we utilize this relatively simple image formation model in order, for example, to filter images? So somebody gave you a color image. It tells you that this is a natural way of the inner product of the light source and the normal are being captured at each and every pixel. But the image went through some sort of corruption, for example, MPEG compression, or some noise that was added to the image. And now you need to know your knowledge about the world, your knowledge that an simple image formation model has the following property in order to denoise the image. Was there any question? If not, then please mute yourself unless you have a question. It would really, really help me. So Udi, Roy, if you can, please do that. Who else?
What is the point with denoising here?
The point is that somebody is giving you an RGB image, okay? And I didn't tell you how to denoise the image. I'm telling you that you need to rely on some God-given knowledge of how an image is being constructed, is being observed, in order to use it afterwards to denoise the image. So again, I didn't tell you how to invent your filter. In a moment, I will show you how. But I'm telling you that if you look at the color image and this image does not include any reflections or specularities or something like a mirror, then you can think about it as something which is called the shading image, which is nothing but the inner product between the normal and the light source direction, times a scalar which is called the albedo, and the albedo is the same. For example, if I would look at an orange, okay, so here I have an orange. So all of the orange would have the same row of R, row of B, and row of G, okay? Probably the orange would have row of R really high and row in G and row of B relatively small. So it would be the same scalar that multiplies the same shading image. And if, for example, somebody is now giving me an image of an orange, and obviously the leaf should have a different albedos. And if somebody is now giving me an image like that, what I could do is somehow tune the values of the pixels so that they would satisfy this relation. Okay, so how should I do that?
Ronnie?
Yeah.
On the left-hand side, you have a function of X and Y, which are the pixels of the image. And in the right-hand side, you will have no reference to those coordinates.
So you're absolutely right. The N depends on X and Y, and the alpha does depends on X and Y. So if I'm looking at let's draw it again. If I would look at my orange here, okay, and let me just pick up a different color. So the orange here should have rho, I'm deliberately exaggerating, rho of G equal to 1 inside, and rho of R and B, rho of B should be equal to 0 inside the leaf. And if I'm looking at the orange itself, then I would have rho of R, for example, equal to 1, assuming that the orange is red, and the green and the blue should be equal to 0. So these colors also depend on X and Y, but they depend on X and Y in a segmented sense. And these values, okay, do depend on X and Y. Why? Because the normal, if I'm not looking at something which is not interesting like a plane, if I'm looking at any object which has interesting topology or geometry, then the normal would change at each and every point on this surface. I'm assuming that the light source is the same for the same scene, okay?
So Ronnie, so this is the mathematics that helps us to prepare the colored images for the CNN?
Well, in a moment, we'll see how this one could be fed into a CNN, but assume that somebody is now giving you not R, but rather R plus some noise. So it would be R of X and Y plus some noise of X and Y, or multiplication, or whatever you like. And what would usually happen, and forget about CNN for a moment. What would happen is that your red, green, and blue values would not satisfy this equation, which is written here. And what you would like to do is somehow define a loss that you would fit into your neural network. Okay, so assume that I'm now summing all these losses. So I would like to reconstruct the red, the green, and the blue, given the noisy, let's call it noisy, red, green, and blue, so that at the end of the day, the reconstructed red, green, and blue would satisfy an equation like that. So you can train it with a lot of data, but then you will have a lot of data. In the case of images, it's not a big deal, but in other cases, it is complicated. So you will have a lot of data, and at the end of the day, you will have to define some loss. And now I'm dealing with the image formation model before we are generating the loss. Okay? Yep.
May I have another question? You are stating here that the RGB are independent, but maybe there is some dependency, because it makes sense that, for example, an area with a color of orange will have similar values of R, like an area with, I don't know, in a red color.
You're absolutely right. What I was saying is that the albedo is piecewise constant or piecewise smooth, while the normal varies more rapidly. Okay, so the albedo, for example, the skin has the same albedo almost everywhere. If you're looking at almost anything in your house, usually it satisfies this kind of relation. So if there is anything interesting in the sense of the geometry, then the only thing that varies in a rapid manner, it would be the normal. The albedo is something that varies in a, let's call it, less rapid way. And I'm telling you that some God-given oracle gave you this equation, okay? This is the relation. So, by the way, look at the fact that the red, green, and blue do depend on one another. The way that, I mean, with the image. Within the image, they depend on one another by just having this, something that we call a shading image. So this would be I of X and Y. It multiplies the albedo, and the albedo, I mean, if I have one object here and another object there, so the albedo would be constant here for the red, green, and blue albedos, another one here and another one there. And you're obviously right. This is not, this is something that would not be satisfied perfectly, but as a first approximation, I can think about it as such. Okay, so for a moment, assume that I'm the genie and I'm giving you this, it's called Lambertian shading model. And now what can we do with that? And the answer is simple. What we can do with that is the following. We note that, well, I call the shading image the inner product of projecting the normal to the light source, J of X and Y. And therefore, if I'm taking the gradient of each of the red, green, and blue images, what I'm getting is within, so let me do it here. So the gradient should be the gradient of both terms, okay, the albedo and the shading image. Now I know that within each object, the gradient of the albedo is constant because I told you that a red, an orange would be orange. So the albedo would probably be constant inside. What would vary is probably just the shading image inside the orange. So this term would probably be equal to 0, at least when we don't jump between objects. And this would be the only effective term that we would look like. So we see that within each object, the gradient of the image equals to nothing but the gradient of some shading image times some constant. So now if I'm using this as my optimization term, okay, plus that, and I'm also reconstructing the shading image along the way, it appears that I can do some magic. And if you remember the video that I have shown you in the previous lecture, in which we are denoising the depth image by aligning the normal to some shading image, this is exactly the equation that we used. So again, this is an image formation model in which that we can use in order to do something which is called unsupervised training by taking this kind of equation and feeding it aside from the big data that we are feeding the network. So my image formation model basically tells me that within each and every object, the gradient of the red, the green, and the blue should have the same direction. It doesn't tell me what would be the size of these gradients, because for that I need to know the albedo. And if I know the albedo, I should also know the sign. By the way, surprise, surprise, when I'm jumping between two objects, so if I'm having one object and another one, then along the boundary between the two objects, the gradient should also align. Okay, why? Because I have huge jump in the intensity of the image. So this is an image formation model that we can use as an unsupervised measure to train the networks.
Ronnie?
Yeah.
But when you're jumping between, when you're moving on the border between two objects, the term that you neglect, the left one, the equation of the gradient of R is not 0, because you're moving between two objects with which their albedo might.
You're absolutely right. You're absolutely right. Who was that? This is
Yuval.
Again?
Yuval. My name is Yuval.
Yuval. Okay. So what Yuval is saying that when I'm jumping between the orange and the background, there will be a huge jump in the gradient of the albedo. And Yuval is absolutely right. But let's see what happens with this conclusion here. The fact that I'm having a huge jump in the albedo between the orange and the background would actually also cause the gradients to have the same direction. The direction of the gradients would be nothing but alignment of the gradients along the boundary. Okay, so the gradients of the red, green, and blue should also align. So Yuval is absolutely right. Within the objects, the three gradients of the three colors should align. Between the objects, the gradients should align because of a different reason. So what I can conclude from here is that the gradients of a natural image without specularities should always align, okay? And this is, again, this is an oversimplified assumption, but it's a really powerful one if you don't have any other information to deal with your objects. Let me jump ahead a little bit and let me give you a very, very simple example in which we are in which we look at an image and we try from the image to reconstruct the shape that we are looking at. So first of all, just some reminders. If we are looking at the surface, and let's assume that the surface is a very simple function. So the surface is nothing but is mapping the xy coordinates of parameterization to the xy and z of xy. This is called the graph of a function or a surface, okay? And specifically, we said that the shading, the Lambertian shading model is nothing but a projection. So if this would have been my surface Z, and this would have been my normal of the surface here, and assume without loss of generality, I'm taking the lights of direction to be from above, then the image that I'm looking at is nothing but the inner product between the normal and the lights of direction. So it should be the cosine of this angle. Let me prove that. So what is the normal of a surface? The normal of a surface is taking on the surface two tangent vectors. For example, the derivative of s with respect to x, okay, which is nothing but, if I'm taking the derivative of x with respect to x, it would be 1, x with respect, y with respect to x would be 0, and z with respect to x would be z of x. Okay, and similarly, the derivative of the surface with respect to the parameterization y would be 0, 1, zy. You probably remember that from calculus, but if not, I'm now reminding you. And the cross product between these two vectors, so again, if I'm looking at my image as a function, sorry, at my surface as a function, and these are the x and y coordinates, then projecting these coordinates onto the surface, I would travel along this direction here and that direction there, and I would have my two tangent vectors. And the cross product between these vectors would give me a vector along normal to the surface. And this is how you do the cross product. It would be putting the x, y, and z coordinates at the top, and then putting the derivative according, one vector here and another vector there. And the outer product would be nothing but the determinant of this matrix, which is nothing but, it would be the x direction times this part of the equation, then the y times that part, etc., etc. And you know how to do it. It would be the x times 0 times zy plus zx times 1. So it would be minus zx. Then the same goes for y, and then for the z, what I'm getting is this part, and I'm basically getting only 1, okay? So this is the non-normalized normal, and if I would like to normalize that, I need to write it as that guy divided by what? By square root of 1 plus zx squared plus zy squared. Are you with me? This is something that you should have learned in your basic calculus, but if not, then now you know how to do the cross product between two vectors, and these two vectors are on the surface, and the result is the normal vector, which is normal to the tangent plane. This is called the tangent plane to the surface at this point, okay? So I computed the normal, and now what do I do with that? I have an equation. And now I'm also telling you that I'm assuming that the light source direction is shining from above. So this is just for this specific case where the light source is given from above, and this is my surface. So I have my surface. This is the normal of the surface. I've computed it here, so this is my normal of the surface. This is the light source, and the inner product between them, I have 0 times zx and 0 times zy, which is equal to 0, and I have 1 multiplied by 1, and this is the output. So this is basically the image that I'm getting, I of x and y at each and every point, if the albedo would have been 1. So I'm simplifying the discussion for an albedo which is equal to 1. And this would be my image. Now, here comes the following question. Can I take the image and from the image go back to the surface? What do you think?
No.
Who said no?
Well,
Yuval Hitman. Thank you, Yuval. Why not?
because if you goes back to the equations that you show in some previous slides, you can't come back from the cosine multiplied by the albedo back to the xy representation.
Well, look, I simplified things for you, okay? I'm telling you the albedo is given. It's always 1, okay? It's always 1. And the intensity is equal to this equation. And the question is, can I solve this equation in order to extract z out of the image, okay? Now,
everything that it's on the unit sphere might be suited to the solution, so you can find exactly what was there.
Let me, you are right, but let me give some better motivation and something that my good old supervisor, Freddie Brookson, told me. If, first of all, go to the one-dimensional case. If you understand things for the one-dimensional case, then probably you would also understand it for the two-dimensional and higher dimensional spaces. Okay, so if we look at the one-dimensional case, then what I'm basically telling you is that let's write it in a very simple sense. I'm telling you, let's even square the image. So there is a function here of x and of x, okay? And what I would like to do is find 1 plus the derivative of the function square, okay? So there is, I'm squaring the derivative of the function. So since I don't know if my function is going up or down, then I have a problem here. Okay, this is if I rearrange terms. So we got this equation, okay? We got this equation. And if I rearrange terms, and remember the x and the y, the I and the z depend on x and y. And if I rearrange terms, what I'm getting is this equation here, okay? So if I'm looking at this function, or that function. Now, let me try to do it. Then both of them would have the same absolute value of derivative when I'm looking at it, okay? So if I'm looking at the absolute value of the derivative of this, of the blue function and the green function, they would be the same. So I will not be able to distinguish between them, okay? But still, under very generous conditions, it appears that you can do the reconstruction. Okay, so you can, in some cases, reconstruct z. For example, if I'm telling you that z is convex or concave, then probably you can do something. And this kind of equation is called an iconal equation. It's called an iconal equation because it has to do with the way that waves are propagating. And if you think about it for a moment, if, for example, I would have chosen my intensity to be the same almost everywhere, I mean everywhere, and assume without loss of generality that it is equal to, I don't know, to something that is giving me 1 here, okay? So what kind of functions have gradient of z equal to 1 almost everywhere? Are you familiar with such functions? Anyone?
And distance
linear.
function.
This was linear because you said almost.
So there was Alon and Ido, so linear, yeah, linear, but
Balls,
you said,
maybe
almost, so
spatial.
piecewise linear.
Efrat, can you say something?
Maybe round shapes, like balls or spatial balls.
Well, first of all, let me give you a very trivial example. For example, I can look at the plane, and the plane gradient is equal to 1. So this is one way of finding, I mean, if I would just look at a slope like that, then this is a solution to the equation, okay? But now I also have some, we call it boundary conditions, some points at which I think that I know the distance. For example, let's assume that I'm telling you that in the plane, all these points along this set I have the distance which is equal to 1. I have the z of x and y equal to not 1, but rather 0. So how would the solution of gradient of z equal to 1 look like? Anyone?
It would be an SDF, sign distance function.
Exactly. So what Nadav is saying, hi Nadav, is that it would be, for example, a distance function, because if I'm, so think about a cone. So I will now draw my circle like that, and this would be a sign distance function, okay? And the gradient, if you think about a one-dimensional case, so if there would have been 0 here and 0 there, then this would be a gradient 1 fitting to this point here, and there would be another gradient 1 fitting to the point there. So the gradient, the slope here and there, the absolute value of the slope would be 1, and this would be the smoothest function you can think of that satisfies the aconal equation, okay? Now, solving the aconal equation is really, really important in graphics for many applications. For example, if you'd like to know how light is propagating through some interface, if you'd like to know how to navigate a robot in some rough terrain, when and many other applications. So it is a really important equation. Probably we will get to it. I don't know if we'll have time, but we'll get to methods of solving this kind of equation. Okay. So this is Connell-Laconen equation. Remember that if you know how to solve it efficiently, then you can compute a sign distance function from a curve in 2D or a surface in 3D. It is a very nice and elegant implicit representation of the zero set, of the set of points that I have now given you. And we could work with that. Okay, so
I have another small question. You said that regarding the ambiguity in the equation, if we assume smoothness of higher derivatives, then we have only global ambiguity of the sign, right? I mean, in your drawing, you had opposite.
Let me give you the formal answer, which would probably not satisfy you. And then let me tell you that the answer is complex. It's not that trivial. So yeah, there is a family of solutions to this kind of equations, which are called viscosity solution. Okay, viscosity. Viscosity solution is our ways of solving this kind of equation that would give you the smoothest possible function in all its derivatives. If you like, I mean, I don't want to throw any more terms now. So this kind of equation, I mean, if you look at these 2 points that are equal to 0 and searching for a solution here, then this would be a legitimate solution, okay? Almost everywhere, my function gradient is equal to 1, besides these points, okay? Okay, these points I have reflections. Now, among all these, and all of these solutions are called, you can treat them as something which is called weak solutions, and then you can also fit in the higher order derivatives. But among all possible solutions, the one that would give you the smoothest one would be the viscosity one. And it would still not solve the problem because, again, as you said, you can have a sign distance function which is positive and another one which is negative. So up to a global sign, you would still have to choose between them, okay? But up to that point, the viscosity solutions do know how to treat these kind of equations. And I really hope that I will have time to just give you an intuition of how these kind of equations are being solved. I mean, how to numerically solve them. And then, by the way, if you understand that there are tricks, numerical tricks to solve these kind of equations, it appears that you can feed them into a network that would give you really nice approximations to solving this kind of equation. I don't remember if I mentioned that. I think I did, but Moshe Lichtenstein solved this kind of equation with a neural network in a very efficient and accurate way. Okay, so when we are talking in computer vision, for example, about somebody giving you a model and you have to solve it, usually what somebody is giving you is a functional, okay? He's telling you, look, this is your model, but now let's satisfy this model over the whole image. So what we would probably do in a natural way is define this as some norm and integrate it over the whole image, okay? I mean, if you'd like it to be linear at the end, then you square it here or something like that, and you would probably square it there. It would not help you much, but this is called a functional, okay? And the functional, Ido, are you recording? Yeah, now you're recording. And the functional is basically, let's call the functional here. And the functional is basically a function of my function z of x and y, and its derivative, okay? Its derivatives, zx, zy, etc., etc. So this is called the functional. So the functional is getting as an input a function and its derivative, and the output would be a scalar, okay? So the functional is getting as input z and z of x, etc., etc., and the output would be some scalar function. And my question is, among all possible functions, which would be the one that would minimize my functional, okay? Now, in order to understand how to deal with things like that, we have to resort to something which is called calculus of variations. Now, it is true that neural networks usually rescue you from resorting to calculus of variations, but in order to understand, and in order actually to help your networks occasionally, you need to understand that. So this is where we will invest, I would say, about 20 minutes or even a little, probably half an hour to understand what is calculus of variations. So the idea, let me go to the main idea, and let me do that. Let me use my equity here. So the idea goes as follows. When we are talking about functions, usually we are mapping, I don't know, let's assume R into R. So this is one-dimensional function. So we basically take points in R, D, for example. So these are points, or a smooth way of looking at RD, and mapping them into some value in R. If, for example, we are talking about R1, then we have our function that we now study and explore, okay? In high school, what we did is we took a coordinate x and we changed the values of the function about this coordinate x, and according to the change of the function, we decided whether the slope was negative, whether the slope was positive, or if we are at an extreme point, a maximum or a minimum. Now, let's take the other idea. The other idea was a functional that is taking not a point in RD, but rather functions, okay? So it takes the function and its derivative, and the output would be a scalar value. So what we will do here is we will revisit the whole notion of adding some epsilon to my coordinates. Instead of adding an epsilon to my coordinates, what I will do is I will take my function and I will add to my function epsilon times something which is called a variation, okay? A smooth function, eta of x, which would be my variation. So again, if in regular calculus I've added an epsilon to my coordinate, what I have to do here in the calculus idea, in the functional idea, is to add an epsilon times a function. Again, let me repeat it again. I have my value in my coordinate system here, x, xy, xyz, and in order to explore what is going on to the function, I have to perturb it a little bit about a point. Now I have my function as my coordinate, and in order to understand what is going on with the functional, what I would do is to perturb it a little bit, and at the end of the day, when I will perturb it, what I got here at the end of the day is saying that, look, if you're at an extreme point, if the derivative of f with respect to x equals to 0. So this is a local condition that would tell me if I'm at a local maximum or a local minimum, okay? A local maximum or a local minimum. The output of taking the derivative with respect to, in a moment we'll see, with respect to the epsilon, would be a function, a condition on this function. Now this condition would be for each and every point of this function, such that if the condition is equal to 0, so it would be a differential equation. So if, for example, let's let's remind you something that you know before. So if, for example, I know that my gradient of z, absolute value, minus some function g of x and y equals to 0, which is nothing but the iconal equation, then I know that I'm at a local extremum of this functional. Questions about the principle, the idea of what we are going to do here. So let me add some more noise to the game. So assume that I have my function z defines between x equal to 0 and x equal to 1. I would now add my variation, my eta function, to be such that it would be 0 at the beginning. So it would be a smooth function. And this would be my eta of x. Okay? So this would be my perturbation, my variation to the function in the set of all possible functions. I know this is difficult to comprehend. And if you are better in algebra, then think about z as being a vector. And the variation would be adding a small epsilon, a different epsilon to each and every element of this vector. But I think it's a more complicated way of thinking about it. I think the continuous way of thinking of it is a little bit more intuitive, okay? So translating calculus into calculus of variations, translating values of functions into values optimizing for values of functionals is what we are after now in this discussion. So let's see if we can do something intelligent about it. So again, calculus of variations is the idea of taking a function of functions, okay, and the derivative of the functions, and asking among all possible functions in the space of functions, which one would give me an optimal value for this functional. Now, this equation, this local equation, is called the Euler-Lagrange equation, and this is how it looks like for this specific case. In a moment, we will prove it, okay? Now, the moment we write partial derivative, so there are two things here. There are full derivatives and partial derivatives. Let me remind you the difference between partial derivatives and full derivatives. Partial derivatives would mean, let me change color here, would mean taking this guy as a symbol, let's call it, I don't know, let's call it Q, okay? And now what I'm doing is replacing Q here. And when this operator is working over F, it would be like taking the full derivative according to Q of F and U and Q, okay? So this would be equivalent to taking the partial derivative of F with respect to U of X, okay? It would be taking the term U of X and treating it as a whole. Next comes the full derivative according to X. The full derivative according to X has to work on U of X, and now instead of Q, we plug back U of X, okay? So let's do an exercise. Let's apply this guy to the following. Assume that U of X is nothing but, let's do UX squared, okay? So we have integration of UX squared dx. I think in the previous lecture, I told you that this is called the Dirichlet energy, but it's not important. I mean, these cursors are not important. And now I would like you to compute the Euler-Lagrange equation of this functional. What would be the output? What would be the outcome? Please take a moment and do the math. In order to motivate you, I will give 1 point to whoever is giving the right answer. We will distribute some points along the semester. 2 points.
UXX equals 0.
Who is that?
It's me, Boaz.
Boaz. Okay, Boaz. Please send me an email. So Boaz Cole is saying the following: UXX equals 0. Now, obviously, if you have masters in high energy or applied physics or information theory, then probably you should know that. But let's do the math. Okay, so first of all, we take UX squared and we take the partial derivative according to UX. and then what we get is 2 times ux, okay? So this would be the result of taking partial derivative with respect to ux of ux squared. It is treating ux as q, and q squared derivative is nothing but 2 times q. And now I'm taking a derivative of this part with respect to x. And the output would be 2uxx. Now, since I need this equation to be equal to 0, I can get rid of the 2. And indeed, this is the equation I am getting. Uxx equals to 0. And this is a very nice equation. I mean, if I'm giving you some initial function, for example, and I would like to use this as some sort of a way of optimizing this function, we'll talk about it in a moment. Okay, so this is the idea behind calculus of variations. And let me give you another motivation of why we can use calculus of variations. And in fact, let me tell you that in a discrete setting, each and every network is actually doing calculus of variation for you. And let's think of the following idea. Assume that I have a function. Okay, so this is my one-dimensional function. And somebody is giving me the value of a function at a specific point x0. How would I use the fact that I can, so this is f of x. How would I use the fact that I can take a derivative of this function in order to find the local minimum of this function? Any ideas for those of you who learned optimization?
Descent?
Again?
Gradient descent?
Yeah, so who is that? Please say your name.
Nadav.
Nadav. So Nadav is saying gradient descent. So here I know that my gradient, my derivative is negative, and here I know that my derivative is positive. And in order to get from x0 to my, let's call it x star, what I need to do is somehow shift my x from left to right, and here from right to left. So in fact, writing an equation of, let's write it in iterations, and then let's write a differential equation for that. Xn plus 1 equals to xn minus some, usually we call it the step size, so let's call it dt, times the derivative of my function is a gradient descent process, okay? And writing it as a differential equation, I can write it as xn plus 1 minus xn divided by dt, and taking it either to the limit of n of dt goes to 0 and n goes to n plus 1, I would have that the derivative of x with respect to t should be equal to minus f of x. Okay, and this is called the gradient descent process, and it would take the point x0 into x1, and then x1 into x2, x2 into x3, and eventually I would probably wobble about this point, and there are ways to stop that. And if I start from the other side of my valley, then I would go into the right direction, and this is a way of using gradient descent of finding the local minimum of this function. The same idea, now this is important. So this is gradient descent, and those of you who didn't learn optimization, please go and search for what is a gradient descent process. It's basically the main idea behind neural network. This is how in neural network you use stochastic gradient descent. So those of you who ever learned anything about networks should know this process. Now, what is going on with functionals and the Euler-Lagrange equation? One can look at the Euler-Lagrange equation in a sense as the first variation of this functional. I mean, this is the way to move your function so as to minimize the functional. So if, for example, I got at my, and we write this one e of u and its derivative, then the first variation would be nothing but e. This is how we denote it. So this is the full analogy, in full analogy to the gradient descent. And here should come this equation with either a minus or a plus sign. It depends if you'd like to propagate it to the maximum or the minimum. So thinking of the previous example of minimizing ux squared dx, what would be the gradient descent? Mr. Cole, what would be the gradient descent?
Minus uxx.
So it wouldn't be minus, but rather plus uxx. And this equation is known as the
משוואת חום.
Heat
Heat
equation.
equation.
Yeah, heat equation, משוואת חום. So this is nothing but the heat equation. The heat equation, and the reason it is called the heat equation, for those of you who don't know this equation, is because it takes each and every point and distributes, I mean, it takes a given profile. Assume that somebody is giving me a function with two boundary conditions, and what it would do is you can actually see it would move each and every point so that it would be equal to its average. Please work this out, this intuition, and in fact you can show that the solution to this equation after a while is nothing but taking this initial, let's call it u0 of x, and u of t, u at time, let's call it u at time equal capital T, is equal to u0 of x times what? I mean, how do I get the condition at time t? Anyone knows? What is the solution of the heat equation?
Heaviside function or something like that?
No. You have to convolve it with a Gaussian whose variance is equal to t. And I think that we could actually give it as an exercise, but remember that this is the solution, okay? So the solution to the heat equation is nothing but remember what we started from. This
Sigma
was
square is equal to T.
Again? Sorry?
Sigma square is equal to T.
Sigma square is equal to T, thank you. But remember what we started from. We started from minimizing the sum over the derivative of the function. And it should not be a surprise that the most efficient, in some sense, way of getting your initial given function to be as smooth as possible, which is nothing but something which is measured here, is by this kind of equation, okay? And since the Euler-Lagrange equation, the heat equation is a linear equation, there is a remedy, there is a solution, which is nothing, which is given by nothing but the convolution, and convolution obviously relates to convolutional neural network. So if somebody is giving you a function and would like to smooth this function as efficiently as possible, probably if you train a network and you look at the layers of the network, they would do something like that. They would iteratively do convolution with a Gaussian. It would be interesting to train a network and see that. Let me try before the break, see some other examples. So now I'm taking a curve, and this curve is nothing but a function, okay? And rather than just integrating over the yx squared as we did before, now what we do is we integrate over the x squared plus dy squared. This is the Euclidean arc length. And now let us divide and multiply by dx, so it would be equal to nothing but, so I'm integrating over that, so it would be these kind of chunks here. So it would be dx squared plus dy squared. Now dividing and multiplying by dx, I would get exactly what is written here. So dx squared divided by dx squared would be 1. Roughly speaking, dy squared divided by dx squared would give me yx squared, and the x goes outside of the parentheses, and I'm getting this as a way of measuring the length, the Euclidean length of the curve. So if you again apply this idea of taking the partial derivative with respect to u, that in this case doesn't give us anything, plus, was it plus or minus, minus d over dx and partial derivative. So here it would be y, and here it should be y of x. Okay, if I apply this guy to that guy, what I would get at the end is nothing but this equation. Okay, so we see that again, in the nominator, what we get is uxx equals to 0. And indeed, this is if, and in the denominator, we get something which would always be larger than 1, because yx squared would always be positive, okay? So if, for example, we'd like to explore what would be the solution of fixing my function at 2 points, and then asking what would be the curve of minimal length, what I would get is that yxx should be equal to 0, which means that yx should be equal to a constant, which means that the straight line is the shortest path connecting 2 points. So this is Now, obviously, I told you that this is just a local minimum, but if you accept the fact that in this specific case, the problem is convex, then which needs to be proven, then I've proven to you that the shortest path connecting 2 points is nothing but a straight line, okay? And this is the way of actually showing that if we indeed apply this one to this one, what we get at the end is this value that should be equal to 0. More than that, if we now take y and take this guy to be, so now I would like to use y and change it according to that equation. It appears that this equation is called the geometric heat equation, or is related to the geometric heat equation. In fact, it takes the curve and it moves it as follows, where S is the Euclidean arc length. Let me try to push the proof before the break. I know that you need it. I need it as well. So in calculus, what we did is we added an epsilon to my function. We took a derivative with respect to epsilon. And now we complicate things. We add some constant eta. And we would like this equation to hold for every eta, okay? And at the end of the day, since we wanted this equation to hold for every eta, obviously the condition for a local extremum would be the derivative equals to 0. Okay, so this is complicating calculus. And as I told you, you can look at the derivative as a way of producing gradient descent. Now let's take this intuition into functionals. Okay. So how do we do that? Again, this is just repeating what I've said before, so I will. But let's repeat it. So what I would do now is I would take my functional here, and I replace each and every u by u tilde, which would be nothing but u plus epsilon times my variation. Now, when I'm taking the derivative with respect to epsilon, I would like my my derivative of the functional with respect to epsilon to be equal to 0 for every smooth function that I'm adding to my, for every variation that I would add to my function. So again, I have my function, and somebody is telling me, look, this would be your variation. So this would be my eta. And for each and every eta, I would like my derivative of the functional with respect to epsilon to be equal to 0. And I'm telling you that for this specific simple case of a one-dimensional function, this is what we are getting, okay? And obviously, I can use it as a gradient descent with a minus sign if I would like to go to the optimum. Okay, now I will tell you that, and then we'll take a 7-minute break. So how do we do that? Let's take the full derivative of f of u tilde, and obviously the derivative with respect to epsilon. So remember what I have here is I have ux plus of x plus epsilon times u eta of x, and epsilon is a scalar. So when I'm taking the derivative of f with respect to epsilon, what I have to do here is first of all take, if you're familiar with the chain law, okay. So first of all, I'm taking the partial derivative of u with respect to u tilde. So what is written here is nothing but a shorthand notation of partial derivative with respect to u tilde of f of u tilde and whatever. Okay, and here the same goes for u tilde prime for the derivative. But if I'm taking the derivative with respect to epsilon, what I need to do now is take here the full derivative of u of x with respect to epsilon. Okay, and if we do that, what we have here is the derivative of u tilde with respect to epsilon would give us nothing but eta. So remember that we write it, u tilde is equal to u plus epsilon of eta. And if I'm taking the derivative, what I would get here is nothing but eta. And the derivative would be nothing but eta x. Now what I would do is I would apply my way of doing integration by parts in order to change the derivative from eta to u, okay, which is equal to what we have here. You remember integration of u v prime equals, so this is integration by parts. And remember that without loss of generality, what I did is use the fact that my eta of x zeros at the boundaries, okay? So this guy would be nothing but 0, so it goes away. And what I have at the end is the following. I have exactly what I have told you would be the case, which is nothing but the Euler-Lagrange equation. Now, let me ask you the following. So again, this is a proof that this is indeed the Euler-Lagrange equation. Now, let me ask you the following question. What would happen if I have my curve C of P as being equal to x of P and y of P? Okay, how would the Euler-Lagrange equation look like? What would happen if I'm looking, so this is again, this is a mapping from a one-dimensional creature to 2D. Okay, what would happen with my scalar image, I of x and y? I mean, I now define some functional over the image and its derivative. And again, the image is a mapping from R2 to R. So what would happen when I'm working with curves? And what would happen when I'm working with more than one-dimensional functions? Okay, so think about it. Obviously, it would influence your functionals. And the extension, I mean, the taking it from 1D to 2D is not that complicated. It is technical, and I still debate whether we should do it in the homework or you should, or I think that Ido would probably mention it in class. But this is a very simple way of doing this construction. So let's take a 10 minutes break. So 11:38 we are back. Okay, so 11:38, be back. Are you okay with the break or?
Sure.
No, but if you tell her it's
Okay. Okay, so let me recap. So what we did is we we tried to come up with a condition that would look at the functional and would give us at the end something that we call the Euler-Lagrange equation. And I told you that the Euler-Lagrange equation, or at least the first variation, part of the Euler-Lagrange equation, can be used as a gradient descent mechanism in order to optimize a function. So the way to look at it goes as follows. What we did is we look at the limit of this equation. So this is called the first variation. And what we got at the end is that this guy needs to be equal to 0 for each and every eta. Okay, and this is called, I mean, equating this part to 0 is called the Euler-Lagrange equation. But let's look at it from another perspective. What I'm basically doing is asking for each and every eta, what would be the inner product, because what is going on here is integration of eta times some other function, let's call it g dx, okay? And this is nothing but the definition of g eta, okay? So this is nothing but the inner product between this part and that part. And we know that choosing the direction, if now I limit the norm of my eta to be 1 and I'm minimizing eta with respect to this norm, so assume that from all possible variations, I'm looking for the one that would extremize this variation, then indeed, the direction at which I have to go is this g function. And moreover, so the direction would be the normalized g function. And in fact, we can actually choose this g function in order to determine our gradient descent. Okay, so this is a way of looking at calculus of variation as a way of producing a gradient descent mechanism. Okay, now some examples, or not examples, some way of looking at it. So regular calculus provided us with a gradient descent mechanism, and calculus of variations provided us with a different gradient descent mechanism. Here the mechanism works on the coordinate, and here the mechanism works on the function. Okay, and the examples that I was talking about was, for example, optimizing the length of a curve. Now, not a function, but rather writing it in an explicit form. So it's no longer a function, but rather a parameterized curve. And this is what you would get, and this is what you would get at the end. Prove it. Okay, so this is, I'm not teaching this, but this is it. And again, this is the definition of Euclidean arc length. In a moment, we will get to this equation. In a moment, we will get to the bits and bytes of this equation. Okay. And here are some more examples. What happens when we integrate over the squared of the gradient? So now it's no longer integration over one parameter, but rather over the x and the y parameters. This is, by the way, this was the way that images were processed, I would say, until 1919, minimizing the Dirichlet energy. Then came total variation, which is nothing but reducing the absolute value. And afterwards came sparsity, in a sense, and geometric model. And now it's the era of neural networks, of learning directly from the data. But understanding the basics is very important if you'd like to boost your methods, your algorithms. So again, the output of the result of minimizing the Dirichlet energy, the squared over the gradient of the image, would give you this, the heat equation, as a gradient descent mechanism. And you'll have to prove it. Again, it's not so complicated. It's 2 lines of an equation. Another interesting example is photometric stereo that I will jump over it. I will let you read it at home, and let me just describe the problem. Like the shape from shading that I've shown you before, where you end up with the iconal equation, in photometric stereo, the problem goes as follows. I'm looking at the surface from above. Okay, so this is me looking at the surface. And now if somebody is lighting the surface from this direction, the image that I'm getting would be the inner product of the normal with this light source direction. Okay, so this would be one image. Now somebody has taken this image and removed this light, and is now lighting the image from a different direction. So this would be L2. Now there is another guy that is taking that is lighting the image from a different direction. Assume this one. So this would be L3. It appears that if you take the same image and you take 3 or 4 lighting directions, different lighting directions, then at the end of the day, what you can do is write this functional as your objective. Okay, so it would be zx minus some scalar function, p of x and y, and zy minus. So basically, what you'd like to do is fit your gradient of z to some given function p and q of x and y. Okay, this is what you'd like to minimize. And it appears that if you're using Euler-Lagrange equation, what you're doing at the end of the day is solving the following equation, which is called a Poisson equation, such that the Laplacian of z should be equal to some g of x and y. So again, it would be really, really simple to work it out. This is a linear equation, linear Euler-Lagrange equation. Please do it as part of your homework, because it would let you practice the calculus of variations and what kind of equation you get up at the end. And if you get this equation, adding it as an auxiliary penalty to your functional would probably give you what you need if you have little knowledge about the geometry of the shapes that you are trying to reconstruct in your networks. Let me jump over this one and over that one, and now we are ready to go into the essence of this course, at least from my perspective, and this is differential geometry. So what I do suggest that you would read, there are some really good books. One of them is the Carmo. The Carmo is more or less differential geometry for engineers. So differential geometry of curves and surfaces. There is also Spivak and some others, Guggenheimer and some others that we have listed in the web of the course. And you are welcome to read, I would say, the first 3 to 4 chapters in these books, because it would really give you an intuition from different perspectives of this whole idea of basically finding the right coordinate system in order to solve the problem and finding the invariance of various properties.
Ron,
yeah, in the future
can
readings.
you put all the reading list in the Moodle?
Sure. I saw that Ido is now actually doing it as we speak. Just sent me a message. And it's also in the syllabus of the course. So let's start with the very basic idea of a planar curve. And as I said, the planar curve, C for curve, is a mapping from, say, the unit interval. And here I would use P to be the parameterization into R2. So R2 is the plane. I have my X and Y coordinates, and C is my curve. And P is the parameterization, and it belongs to something between 0 and 1. Okay, we said that the curve is simple if it doesn't intersect itself. So this would obviously not be a simple curve. And we say that the initial point, so let's do a simple curve. So this would be a simple curve. And we say that the initial point where P is equal to 0 is equal to the final point where P is equal to 1. So this is P equal to 0, 0.1, 0.2, 0.3. And now I'm accelerating. And at the end of the day, I'm traveling along this curve. And at the end of the day, I'm getting to the endpoint at P equal to 1. If I'm now taking the curve, so the curve is given as X of P and Y of P, and I'm taking the derivative, we already saw that what we are getting is the velocity or the tangent vector, and we denote it as C of P. Okay, the derivative of C with respect to P would be the velocity vector. And we denote it as T, the tangent with the vector. The unit vector is T with a hat. So we allow ourselves to normalize it and we call it T with a hat. Okay, so these are the basics. Now we would like to measure the length of this curve. And I've shown you before that if I look at this curve and I'm looking at it infinitesimally, and I'm looking at the length of this part of the curve, sorry, I'm looking at the length of this part of the curve, then the length would be dx squared plus dy squared, and I need to take the square root of both. Now dividing and multiplying, for example, by dp, what I'm getting is this equation over here, and in shorthand notations, here I have x p squared and y p squared, and I'm taking the square root of both these guys, and this is by definition what we called as CP, as the norm of CP. Okay, remember that CP was nothing but XP and YP. This was XP. Okay, and this is how we denote a measure of the length of the curve. Okay, we can actually consider this in a differential form. So if I throw away the integral, what I end up getting is that infinitesimal ds is equal to the velocity times the time. Okay, so the change in time times the velocity equals the change in distance. This is something that we're all familiar with when we are doing our measurements everywhere. Now the question is, can I look at the same curve, at the trace of the same curve? So I have my curve here, and it used to be parameterized by P. So P is something which is arbitrary. I mean, I can drive really fast in this part of the curve and really slow here, and then faster here. And the question is, can I change my parameterization the way that I'm traveling along this curve so that the arc length would be the Euclidean arc length? And the answer is definitely yes. What I need to do, I mean, what I know that should happen is that if I'm taking now partial derivatives, then I get, sorry, if I use the chain rule, what I'm getting is that C of P equals to dP over ds. And what I'm getting is that C of P equals to, now what is dP over ds? It is nothing but, I mean, here, from here, we see that dP over ds equals to nothing but 1 over Cp, okay? So we can plug here this guy. And at the end of the day, we see that we got nothing but the unit tangent. If we indeed parameterize our curve by s and take the derivative, then it appears that we are traveling with constant velocity. And not only constant velocity, this velocity equals to 1. So again, if I parameterized my curve by the Euclidean arc length, then the velocity by which I'm traveling along the curve equals 1. Next, let's see.
But Ronnie, if you change the parameterization, you might change the orientation of the curve.
Is that so? Remember, I'm looking at the curve with the same trace. I'm traveling along exactly the same curve. And now what I did is only so it would be C of P. And now what I'm doing is changing P by P of S. Okay, this is just by changing the parameterization. Think about it as a road. And I was traveling along the road with the velocity C of P. And now I'm traveling along this exactly the same road with the velocity C of S. It's exactly the same road. The trace of the curve did not change. The only thing that changed was the way that I'm traveling along this road. So the trace, the points in the plane are intact. They are not changed. And I can travel along this curve by a different velocity, okay? So the nice thing about Euclidean arc length is the fact that no matter how I orient my curve in the plane, I mean rotations and translation, it would always, traveling from this point to this point would always measure the same. But I can think of more complicated scenarios, and we will get to it in a moment. Okay, more questions? Yeah. So what happens when I'm looking at the second order derivative with respect to the arc length? So remember that we had C of S equals 1, okay, the absolute value. And in fact, we can square it. It would not change, it would still be 1. Now, if I'm taking the derivative with respect to S to this equation, the right-hand side would vanish. I mean, the derivative of constant with respect to anything would be nothing but 0. Now, let's look at the left-hand side. If I'm taking a derivative with respect to S, I need to take a derivative of the left and then derivative of the right. And what I'm basically getting is that I'm getting two inner product of CSS, CS, okay? This would be the inner product of the two. So what I'm getting is that CSS dot CS would always be equal to 0, which means that CSS is orthogonal to CS. So if I'm now zooming at the curve, let me zoom in on my curve. This would be my tangent. So this was my tangent, and it is equal to CS. Okay, and the second derivative, CSS, is always orthogonal to the velocity. In fact, this is called the acceleration vector, and the unit acceleration has beautiful properties. It is nothing but, and I'll prove it in a moment, it is nothing but the radius of the osculating circle about each point. So what is the osculating circle? Take 3 points about the curve. 3 points, they always defined a circle. Okay, so I have these 3 points. I don't know why it is deleting. Let's do it like that. These 3 points would always define a circle. The center of the circle will always be orthogonal to the tangent. This is obvious. And the CSS is nothing but 1 over the radius of this circle. Okay, so it is 1 over the radius of the circle in a direction which we call normal to the curve. So it would be normal to the curve to this, in this direction. It would be normal to the curve in this direction. And there are these points which are called inflection points at which the radius of the oscillating circle is infinity, and therefore the value of 1 over the radius of the oscillating circle is equal to 0. So the curvature is a way of measuring how curvy the curve is. So here the curvature would have a large vector. I mean, this is, if you think about accelerating when driving on the curve, and here the curvature would have a small value. And you can also see that the curvature vector is changing its sign from this direction of the curve to that direction of the curve. Okay. So, yeah.
Which 3 points are you choosing?
Just take any 3 points along the curve where the distance between these 3 points is approaching 0. So here you have epsilon1, and here you have epsilon2, and you'd like epsilon1 and epsilon2 to get to 0. And any 3 points that you would get, again, as long as they are tied together, would define a circle. Okay, you can use a Heron equation to get coordinates of 3 points and define a circle. Okay.
Ron, what is the motivation of the acceleration vector?
Remember that when I told you that if you optimize the length of a curve, then I told you that what you're getting at the end of the day is an equation that whose gradient descent looks like that. Okay, so this vector, so if I'm taking a really curvy curve and I'm evolving it, I'm telling it to flow, to propagate, to do a gradient descent according to this equation, which is called the geometric heat equation, it would minimize the length of the curve in the most efficient way. Now, it appears that this equation is also a really strong way of minimizing the length of all the curves in an image. So if you think of an image I of x and y as being a set of all the level sets of all the equal height contours that define the image, then you can apply this kind of a filter to minimize the length of all curves in an image. And this is a really powerful filter that minimizes not the L2 of not the Dirichlet energy, but something which is called the L1. Okay, this is called the TV norm, total variation norm. So the output would be a filter that looks like that. But besides all these filters, the reason that I'm telling you about the curvature and the curvature vector is the fact that you can look at a curve in the plane, and the simplest way of telling whether two curves are similar or not is to plot using the arc length as one argument and using the curvature as a different argument. Okay, so now when I'm traveling along this curve, I would have a curvature which goes from 0 to something high, and then it goes back to 0 here in the inflection point, and then I'm continuing my travel along the curve, and it would go into positive again and negative, and this is called a signature of the curve. So the curvature kappa as a function of arc length is a signature of the curve. If I'm taking another curve in the plane, rotated, translated, whatever, I can travel along this curve and produce exactly the same function, okay, up to the initial point that I've selected, because I need to start from the same point. Now, those of you from the engineering department should immediately tell me, how could I get rid of, now remember that this function is periodic. When I travel along this curve, I go to the original point, and therefore this function is periodic. How do I get rid of shifts in periodic functions? If I would like to compare to
on one interval.
Again, Yuval, say it clearly.
Look on one interval of the function.
Yeah, but I would like to compare it to a different function. So I have this one to produce this graph, and that one, let's plot it in red, and that one.
Use Fourier.
Again, who said?
You can use Fourier transform and look at the phase of the.
So Natan gave me half of the solution. You look
shift
at the
them both to have a phase of 0.
So again, this is Yuval, or
yes, shift both of the signatures to have a 0 phase.
So basically, you get rid of the phase. Okay, so if you take the Fourier transform of both these signals and get rid of the phase, what you get is basically a shift in. You got rid of the shift mechanism, and you basically have a signature of both. But this is important. You also got rid of part of the information of the signal, and this is something that could be vital. It appears now. this is something that I will give you without a proof, that if you take the curvature and the derivative of the curvature with respect to the arc length, then you get a curve which is a signature, and there is no need to get rid of any phase or whatever, okay? And this is called the Cartan observation or Cartan theorem, but this is jumping ahead, and I would like to keep things simple for the time being. But just remember that the curvature as a function of arc length is a signature of the curves. And I have here C1 and I have here C2, and I can produce these two kinds of signatures. So if, for example, you'd like to do your puzzle and and the puzzle has the same color all over the place, and you just want to follow the geometry, this is the kind of signature that you would need.
You can also look at the cross correlation instead of the spectral domain.
But then so Jonathan said that I could look at the cross correlation, but then my complexity goes quadratic. I would like to keep everything linear. But yes, you are obviously right. What I can do is plot one arc length with respect to the other, and then look at how the curvature in curve 1 correlates with the curvature in K2, and then do some dynamic programming, and hopefully find this kind of two linear curves that would do the matching for me. But again, here the complexity goes to quadratic in the length of the curve rather than keeping it simple. And
but Fourier is also n log n and not linear.
Yeah, log n is we call it quasi-linear. You are right. Fourier is quasi-linear. And by the way, getting into this Cartan of kappa s and kappa of s, I keep things linear. But the problem here is that I need to take another derivative. Remember that the curvature is already a second derivative. Okay, and the more derivatives I take, the more noise I push into the system. And to tell you the truth, I don't know many curve matchers that are using third order derivatives, but still it is important to know from a theoretical point of view. Okay,
Ronnie, how do you find the rho?
I didn't say it. Well, rho is nothing but taking the second order derivative of the length with respect to the arc length, and then looking at the magnitude of this. This would be equal to some scalar in the normal direction. Okay, so the scalar would be kappa would be nothing but 1 over rho. Numerically, if I'm looking at a curve that is defined by these points, okay, a polygon, then I can take in each and every 3 points, fit a circle between these points, and 1 over the radius of these 3 points would be an estimation of an approximation of my curvature radius. Okay. The radius of the curvature. So as we said before, this is nothing but 1 over. So we called rho the radius of the curvature. Now I'm debating whether I should get into it. This is too simple. So what I will now tell you is that you can think of taking. Let me just plot some intuition. This is one tangent, and I will ask Ido to review it. Okay, so he will review it. This is one tangent, and this is another tangent, and this is ds. And what you can prove geometrically is that as ds goes to 0, the intersection of this normal and that normal would be nothing but rho. Okay, would be nothing but, and indeed, okay, this is the c of s over ds, where c of s is these tangents, and you can prove that what you're getting is at the end this rho. And indeed, this we call this d theta, so it would be the change. Okay, so if I shift my first tangent here, it would be exactly this d theta, and by simple calculus you can show that. So I will jump over this proof because it is because of 2 reasons. First of all, it is relatively simple, and second, Ido would go over it in the recitation. In fact, you can write the whole idea in complex coordinates, and then you can just take derivative, and you can immediately show that kappa, that indeed, if you take the derivative according to s, what you're getting is this guy. Now, kappa is also by definition d theta over ds. Okay, and theta is nothing but the change of the tangent in time, the angle of the change of the tangent in time. Okay. So what we have goes as follows. We have that the tangent is defined as the velocity. We have that the kappa n equals to CSS, and we know that they are orthogonal to one another. And by definition, this is the derivative of the tangent. So if we write the tangent in its coordinates, and the normal it's in, so this, sorry. So this would be the normal tangent, and this would be exactly the same one, the normal. So if this is x of s, y of s, in order to get an orthogonal vector, what I need to do is write minus y of s, x of s. Okay, so this is writing explicitly the coordinates so that they would be orthogonal. Now, if I now take the derivative of this guy with respect to s, what I would get by definition is yss xss. And this is nothing but, now we know that xss yss is by definition CSS, which is by definition kappa n. So this would be orthogonal to kappa n. So the direction would be the tangent, and the value would be the same scalar, which is the curvature. So what we can do is we can write the derivative of the normal and the tangent as the same equation. So the derivative of the tangent, the equation at the top, is nothing but the curvature times the normal. And the derivative of the normal is nothing but minus the curvature in the tangent direction. And this is called the Fanet equations for curves in the plane. Okay, so there is a nice relation between the derivatives of the normal and the tangent and their derivative with respect to the Euclidean arc length, and this is the equation that relates between them. Okay, now we are ready to relate between the curvature and a general parametrization. Okay, so the curvature is defined as the second order derivative with respect to the Euclidean arc length. And there is also a nice equation that relates the Euclidean arc length to any given parameterization, and this is what is given to you here. And as said before, again, it is relatively simple to prove. All you do is you plug in the normal and the curvature, and you prove that this is indeed how the curvature works. I mean, remember that I told you that if I have two vectors, v1 cross v2, then the way, I mean, two vectors in some three-dimensional space, then we used to write the x, y, and z coordinates. And here I wrote the coordinates of v1 and v2, and then look for the determinant of this function. There is another way of, and the nice thing about looking at the cross product of two vectors is that it would give me the area of the parallelogram that is defined by these two vectors. Okay. Now, if the only thing, and remember that the direction of this vector is always orthogonal to the plane defined by v1 and v2. Another way that we will use is to look at the area of this parallelogram. And in order to get the area, I would just write v1, v2 in brackets like that, okay? So this would be the area of this parallelogram. So what you see over here is the the area of the parallelogram defined by CP. So assume that this one would be CP and this one would be CPP. Okay, and this is by definition how you define the curvature with respect to any given parameterization. And again, I didn't go into the derivation here. It is straightforward. It is given in the book, and I think that Ido would also do that. Okay. So now remember what I told you. I told you that if you're looking at a planar curve, there is a way of looking at the signature for this planar curve. It would be the kappa as a function of s. And this curve is, as I rotate it and translate it, the curve would never change, okay? But I need to know the initial point. In order to get rid of the initial point, what I do is I do this stuff. And in fact, you can prove at home is that you can integrate this curve twice, and then what you get is exactly the original curve up to rotation plus translation. And the reason is that you can see that you get 2 degrees of freedom. One of them would be the rotation, and the 2 others would be the translation. imagine, can you take this whole idea of signatures to surfaces? And this is a great question. The reason it is that it is a great question is that in fact, there is a solution to that. The solution is hidden somewhere in books and papers written by Peter Olver. Let me first of all give you the answer. Nobody has been using, I mean, this is thing that many people have been using. This is less so, but surfaces is something that we know exists, but nobody used. And the question is why, and we will try to partially answer this question. But before that, we need to understand a little bit about surfaces. But before we go to surfaces, let me tell you what happens besides, I mean, beyond rotations and translations in the plane. Assume that I'm looking at my scene from a left direction and a right direction, and there is an object here, okay? So this is an object here. If I look at a really small region of this object as it is projected on the right and the left image, I can approximate, well, the zero order approximation would be Euclidean transformation, rotation and translation. But the second order approximation, I mean, the first order approximation would be an affine transformation. An affine transformation is taking the X and Y coordinate system and multiplying them by a matrix, by any given matrix, okay? And this is called affine transformation. If besides that, I also limit my function, my matrices to have a determinant which is equal to 1, which means that the area is being preserved, this is called equi-affine or special affine transformations. Usually in this, I mean, in my course, what we did is we defined an arc length that would be invariant with respect to this kind of transformations. And therefore, what we could do is take the right image and the left image, apply the equi-affine invariant filters. So I filter this one and I filter that one with the same equi-affine invariant filters. And then, for example, if I would like to do stereo, I would have matched these two images. In this course, I don't think that we will have enough time to get into the affine invariant arc length, but what we will have to do, time to do, is to look at scaling variant. For example, assume that I'm looking at this curve and a scaled version of this curve. And I would like to say that from a distance point of view, getting from this point to that point would be equivalent as getting from that point to that point. Now, since I talked about it in the first lecture, I would expect you to know what to do. I mean, what would be the scale invariant arc length that I would like to invent in order to say that the distance between these 2 points is equal to the distance between these 2 points.
The direction of the gradient.
Again?
The direction of the gradient.
The direction of the gradient, the change in the direction of the gradient, which we said is d theta. And we already know from the previous slide is that d theta is equal to nothing but the curvature times ds. Why? Because the curvature was defined by d theta over ds. Okay. So we know we have, I mean, we need to take the, since we would like to travel in a way that would always be positive as we travel along our road, we need to take the curvature in its absolute value. Okay, so in a sense, what we do is we look at each and every circle, oscillating circle of this curve, and we normalize it to be 1. Okay, which is in a sense a magic way of measuring distances on scale. Now, when we are inventing arc length, we would like our, and we call it reparameterization, we would like it to be invariant. Okay, so independent of the transformation that we are exposing it to. And we also like it to be, so it should be invariant with respect to the, and we also like it to be reparameterization invariant, which means that as we change, for example, from P to R, it should have the same structure. So it should be invariant, otherwise it is meaningless. And then it should also be reparameterization invariant. So changing from P to R of P, I mean P of R, that would at the end of the day give me a new functional, plugging in the Jacobian, etc., should all cancel out and it should have exactly the same structure. Okay, and the question is how to do that. So let's do it for the simplest. What we'll do in this lecture is do it for the simplest example. The first one is the Euclidean one. So the invariant for the Euclidean, I'm looking for an arc length S that would preserve length Why? Because in Euclidean spaces, in Euclidean transformations, length is preserved. So now I'm using the chain rule in order to write S as a function of any general parameterization. And what I'm getting at the end of the day is that is the following equation, which is not surprise. And what I can basically get at the end is that ds equals to nothing but velocity times time. Okay. And again, what we did is started from an invariant property. And after some math, what we got is the good old way of measuring distances that would be invariant to rotations and translations. Now we can take a derivative and a second derivative and ask ourselves how they talk to one another and invent the second invariant, which is the curvature, and create signatures, and everybody is really, really happy. Now recall that the 1/2 here, I mean, the square root here is also part of the derivation, but without it, what we will have is something that would not be reparameterization invariant. I mean, if we throw away the square root here, then changing from P to R, which is in this case is nothing but CR square root dr, would not be the same. Okay, so putting in it here another power would break this relation. Okay, the next one is what we call scale invariant or similarity. Now let's look. So I'm looking for my parameterization tau such that it would be invariant to scaling of my curves. So what I basically would like to have is a way of measuring distances so that the ratio between how I travel on the curve and the oscillating circle and the radius of the oscillating circle would be 1. Okay, if I find a way of traveling along the curve such that this ratio is always valid, then I have found a scale invariant arc length. Okay, and as I do the derivation, I'm again moving from tau to p, and at the end of the day, this is what I would be getting. Why? Because rho is 1/kappa, 1 over the curvature, and at the end of the day, this is what I would be getting. And what I would get is that d tau equals curvature times, this is nothing but ds, I mean velocity times delta s. And indeed, in order to find a scale invariant arc length, what I need to do is look for the absolute value of the curvature. And this is how it works. So this would be rho is the absolute value. And here I also need to put the absolute value. Okay, and this is a scale invariant arc length. So we learned about arc length and about scale invariant arc length. Let me tell you that there is a way to also construct an invariant arc length to affine parameterizations. I will not get into it, although it is not that complicated. And in fact, there is an affine invariant differential calculus, which is really useful in image processing. But what is important is to tell you that everything we talked about curves can be lifted into surfaces. So again, reminding you, what is a surface? A surface is a mapping from a UV parameterization into, for example, R3. So I have X, Y, Z of U and V. So this would be some sort of mapping the UV parameterization to R3. And if I now take du, and so this would be du and dv here in the parameterization space, the question is what would be, so I've taken a du here and a dv here, and the question is what would be the length of traveling. Let me choose a different color. Is what would be the distance of traveling on the surface, which we call ds. Okay. So first of all, let's use the chain rule. Dx square is nothing but du xu. So dx square is nothing but xu du plus xv dv, which is nothing but what you see over here. Okay. So this is nothing but, again, using the chain rule. taking it one step further, we can do it for the x, the y, and the z, and then rearranging terms, we can write it as follows. Okay, where this guy is nothing but the inner product between xu, yu, and zu. Sorry, and zu. Times, let's write it as a vector, as times xv, yv, zv. Okay, so this is the definition of what is going on here. So we see that there is, it's called the bilinear form that is relating between du and dv and ds. Okay, so there is something that multiplies du squared, there is something that multiplies dv squared, and there is something that multiplies the product between du and dv, and this, we call it affine transformation between the du and dv's and ds. You may also know it as the Jacobian, is also called the metric. So this is the way of translating du and dv into way of measuring distances on the surfaces, okay? So G11, G12, G22, G21, and G22 are the elements of the matrix. And usually we write it as in the matrix form as follows, Gij. Okay, so this is called the matrix coefficients, and it translates an infinitesimal displacement in the UV parameterization space into the length on the surface. Okay, it is also called, let me see if this is, it is also called the first fundamental form of the surface. Okay, and usually it is written with this kind of letters. Okay, I think I did my part now. In the next lecture, what we will do is we relate between curves on the, so this is end of lecture 2. In the next lecture, what we will do is we'll also see what is going on with the second fundamental form. I mean, we'll relate everything to curves on the surface, and we relate to something which is called the second fundamental form, and then study and explore the surface S. I mean, if a curve has one tangent and one curvature, if you're talking about, then on a surface, if you look at the point, you may have many curves going through the same points. It appears that there is something common to all these curves. I mean, you can characterize them really, really, really nice. You can project them onto the tangent plane and into the normal direction, and do this at least when the curve is when the surface is embedded in R3. And you can start asking questions about the curvatures of the surface. So this is something that we will learn about in the next lectures. If you have any questions whatsoever, now this is the time. If I'm running, if it's too slow, then I can accelerate next time, or if I'm too fast, then I can decelerate. It's up to you. I'm now yeah.
Ronnie, I have a question about the Euler-Lagrange equation.
Sure.
I think it was in slide 25.
Okay.
Can you please explain why it must be that the term inside the integral, which is not eta, must be 0 and not any function which is orthogonal to eta?
Again, you're asking, remember that what I would like is for every eta of x, I would like this condition to hold. Okay, this is lim epsilon goes to 0. Now repeat your question.
Yes, I'm asking why so you can use any function which is orthogonal to eta to satisfy this condition, right?
Oh, you're absolutely right, but this should hold for every eta. Okay, so remember that
okay.
I can take eta, and I can take eta 1, which is orthogonal in your vocabulary to eta. So this should hold for every eta, and therefore, in order for it to hold for every eta, I need this condition to be equal to 0 at each and every point.
Yeah. Right. Okay. Thank you.
More questions? If not, then let's break here, and I think Ido is after me. Yeah, Ido? or actually we stop this and
yeah, the recitation will be in 6 minutes.
in 6 minutes. Okay, so enjoy the recitation. Bye.